Hello, everybody. So this is my video about infinite series and all the divergence and convergence tests that you can do on them. Because it took me a while to figure out why these tests work the way they do. But after thinking about it for a long time, eventually they all became very intuitive, and I would like to share that information with you. But first, before we can talk about the tests, we need to talk about what an infinite series is, because that also took me a while to understand, because the notation is not something we've ever seen before. So the notation typically goes, so you have a beginning value where n equals some number, in this case we'll say 0, and then you have an ending value, which is often infinity, and so I'll just write an infinity there, and then you have a sub n. And so the first part that we need to understand in order to know what the whole notation is saying is, what is a sub n? Well, a sub n is just a function of n. A sub n could be n squared plus n, or ln of n, or anything, any function of n. And that's just like how f of x is equal to a function of x. Could be x squared plus x, or ln of x, or anything else. You get the idea. And so the main difference here, though, is that while x can take on any real value, any whole number, 1, 2, 3, and also any of the numbers in between the whole numbers, 1.5, pi, e, which can be represented like this. X is inside the real numbers. N, by convention, you can only put whole numbers into n. 1, 2, 3, 4, 5, and you can't put in any decimals. And so n is inside, and this is the symbol for the integers, a fancy z. N is inside just the integers, no decimals. And so, other than that, though, these types of functions act exactly the same. So, like just like how you can put, if we focus on this function f of x right now, if you take f of 2, that means when x equals 2, as in you plug in 2 for every x, and you get 2 squared plus 2 equals 6, a sub 2, and in this case, you still replace the n with the 2, it's just a sub 2 instead of f of 2. That's still equal to 2 squared plus 2 equals 6. And so if you have a function of x like this and an identical function of n, at all whole numbers, those functions are going to be equal to each other because it's the same function with the same input. However, if you do a non-integer like 1.5, you can do f of 1.5, which is 1.5 squared plus 1.5, which is 3.75. However, if you try to do a sub 1.5, you're not typically supposed to put whole decimals inside of n. And so what you do is you round this down to the nearest whole number, in this case 1. And so you get 1 squared plus 1 is equal to 2. And so at the decimals, they do not have the same answer. But at the whole numbers, they will always have the same answer. Yeah, so 3.75 right there. And you can also take the derivative and the integral of functions of n and functions of x in similar ways. So if we choose simple functions for a sub n and f of x, let's have a sub n just be equal to n, and f of x is just equal to x. So when we take the integral of this function of x, what that means is you take the graph of y equals x, and you add up and let's have our endpoints here as well. Let's say from 0 to 3. So you add up all the area under the graph y equals x. And the way you do that is you take these microscopic little rectangles, each of which have a width of dx. So you take whatever the function is at that point, like 1.5, and you multiply it by the width of the rectangle to give you the area of that rectangle. Then you add all those rectangles up. And of mention, if your endpoint is at 3, you're actually slightly overshooting your endpoint because you're going to 3 and you plug in 3 for x, and then you also go dx past that because you're going, that's your rectangle there at the end. Now, how do we integrate a function of n? Well, the way you integrate a function of n is you write this notation. So this is like a fancy S in some other language, I guess. And you have your endpoint down here at the bottom at n equals 0, just like this 0. And then at the top, I don't know why you don't write n equals 3, you just write 3, but that is your endpoint. And so it's saying add up all the n's from n equals 0 to n equals 3. So now an integral of a function of n works slightly differently. And the only difference is that the width of your rectangles is no longer dx. The width of your rectangles is going to be 1, always. And so if you have 0, 1, 2, 3, 1, 2, 3, to integrate the function of n, starting at 0, you find out what a sub 0 is. In this case, it's 0. And so you draw a rectangle that's 0 tall and 1 wide. So that'll be this rectangle. Imagine it's 0 tall. And now at n equals 1, it's 1 tall, and you draw it 1 unit wide. Then at n equals 2, it's 2 tall and still 1 wide. And then at 3, just like here, you're going to overshoot it by 1. So just like here where you overshot it by dx, here you're overshooting it by 1 because 1 is kind of like your dx in this case. And so if we evaluate these, the integral from 0 to 3 of x is 4.5. But the integral here is you just add up all these boxes. So you have your 0 here, 0 plus, and then you have your area of 1, because remember we're adding up areas, area of 2, and your area of 3. And so that's going to give you 6. And so the sum of n from n equals 0 to n equals 3 is equal to 6. And so these will get, these integrals, like the normal integral and then the sum, will give you different answers, but they're doing very similar things. This is just a Riemann sum with a width of 1. So that is what a sum is. It's just an integral, a discrete integral, where the widths of all the rectangles are 1. So now we can start getting into the actual math of it, the tests. And the first test is computation, which isn't so much a test as it is a method. And so there are a lot of tips and tricks you can use to compute certain sums, infinite sums. One of the main ones is if you have from n equals, let's say 1, to n equals infinity, of 1 over 2 to the n, you can actually directly compute this. And so if you write out all the elements of it, So you have 2 to the 1, and then you add 2 to the 2, and then you add 2 to the 3, and so on and so forth. And so the trick here is to say, let's just have this equal to some s. And we don't know what s is yet, but we can figure it out. So if we subtract, so right here we have this. And so using the rules of algebra, we can subtract 1 over 2 from both sides. So we get s minus 1 over 2 is equal to 1 over, and then 2 to the 2, plus 1 over 2 to the 3, plus 1 over 2 to the 4. And here is a trick. So if you have s minus 1/2, you can take out a common factor from all of these. And so a factor that all of these share in common is 1 over 2, because this is 1 over 2 to the 2, 1 over 2 to the 3, 1 over 2 to the 4. So let's pull out a 1 over 2. So now you have 1 over 2 there, plus 1 over 2 to the 2, plus 1 over 2 to the 3, and so on and so forth. And if you realize this 1 over 2 plus 1 over 2 to the 2 plus 1 over 2 to the 3 is our original s. It showed back up. So what we showed here is s minus 1/2 is equal to 1/2 s. And so now we can continue doing algebra. You have s minus 1/2 s, and I'll move the 1/2 over, equals 1/2 s times 1 minus 1/2 equals 1 over 2. S is equal to 1 over 2 minus 1, or just 1. And so we managed to show that the sum from n equals 1 to infinity of 1 over 2 to the n is equal to just 1. And there is a general pattern that these types of sums will match. And I'll let you guys prove that if you want to. But the sum from n equals 1 to infinity of 1 over a to the n, where a is just any number greater than 1, this is going to be equal to 1 over a minus 1 for a greater than 1. And so let's remember this, because that will be useful later. So now on to our first real test, the divergence test. And so what does the divergence test tell us? So the divergence test says that if the limit as n goes to infinity of a sub n is not equal to 0, it diverges. If it is equal to 0, it may converge. And so why is this? Why does it have to diverge if the limit of a sub n is not equal to 0? Well, think about it like this. So if you have the sum of an infinite number, because remember, we're adding up infinitely many of these, of a sub n, and a sub n never gets closer to 0. It's always, it always stays bigger than 0, even if the limit of a sub n is equal to like 0.00001, no matter how many zeros. You're adding up, and that's as small as a sub n ever gets. You're adding up infinitely many of them. And so 0 times 0.00001 times infinitely many of them is still just going to be infinity, meaning that the sum diverges. It shoots off to infinity. However, if the limit of a sub n is equal to 0, that means it has the potential to converge, but it doesn't necessarily mean it will converge. There are series, such as 1 over n, that the limit is 0, but 1 over n famously diverges. And so now that we have the divergence test out of the way, let's go to the integral test. And so the integral test builds on what we just talked about when we introduced a sub n as a function. And so if you have a particular function of n, let's say 1 over n squared, and you can rewrite this as a function of x. F of x equals 1 over x squared. And so remember, at all whole number values of x, 1 over x squared and 1 over n squared are going to be equal to each other. They're going to be the exact same expression. 1 over 3 squared is equal to 1 over 3 squared. And so if we integrate both of these, so we take the sum of 1 over n squared and then the integral of 1 over x squared, let's draw what those pictures look like. So the graph of 1 over x squared from 1 to infinity and from n equals 1 to infinity, you're going to add up all the area, not including over here, from x equals 1 to infinity. And let's assume we already know this converges, because it does. And so if we draw the rectangles of 1 over n squared in here, we're going to find that they are always smaller than the corresponding value of x. Because here, you're missing all this area, and you're missing this, and you're missing that, and you're missing this. And so 1 over n squared is always smaller than 1 over x squared, except where they're equal to each other, which is only at whole numbers. And so if we know that 1 over x squared converges, then we know that the sum of 1 over n squared also has to converge, and it has to be smaller, because you're always missing this area. Now, this only applies if f of x is always decreasing. Because if we say that f of x is equal to sine of x, for example, that function looks like that. And so if we draw all the rectangles on it, we're going to get this rectangle and that rectangle, that rectangle, that rectangle. And notice, some of them are bigger than f of x, bigger, bigger. Some of them are smaller, 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 but it's never going to settle down. And so if f of x is continuously decreasing and it is convergent from some point to infinity, that means the corresponding sum of all a sub n, it also has to converge, and it has to be smaller. So now we move on to our next test, the comparison test. And so the comparison test is quite a bit like the integral test. And the comparison test essentially says that if you have a nasty looking a sub n, like 1 over n squared plus 5n plus 2, I mean, like, I don't know how to compute that. I don't know if anybody knows how to compute that. But you don't have to compute it to know if it converges or not. Here's a trick you can do, and it's the comparison test. And so now notice something. So we already know that 1 over n squared converges. So this converges. And notice that 1 over n squared plus 5n plus 2 is always going to be smaller than just 1 over n squared. So why is that? Well, it's because this denominator is always bigger than 1 over n squared. So if the denominator is always bigger, that means the number is always smaller. And so if you take, like, for n equals 1, right, 1 over 1 squared, which is just 1. And then for this one, you have 1 over 1 squared plus 5 plus 2, that's 8. Notice, 1 over 8 is smaller. And if you do 1 over 2 squared, That's going to be 1 over 2 squared plus 10 plus 12. This is going to be smaller than that. In fact, they're always going to be smaller. And so if we know that this one converges, then one that is smaller than it always also has to converge. And it also goes the other way. If you have another sequence that you know diverges, the famous harmonic series that diverges, then if you have another function like 2 over n to illustrate it. So if you have 1 over, and let's plug in 1 for them. So you have 1 over 1. That is smaller than 2 over 1. If you plug in 2 for n, you get 1 over 2, and that is smaller than 2 over 2, and so on and so forth. This is always going to be bigger than this. And so that means if we know this diverges, we know that something that's always bigger than it also has to diverge. And so the comparison test works both ways. If you have something that converges and you have another one that's always smaller, that smaller one has to converge. If you have something that diverges and another function that's always bigger, you know that that one also has to diverge. So now let's go on to the limit comparison test. And so there's 3 cases in the limit comparison test. And so if I'll go through them one at a time. So if you have 2 infinite sums, a sub n and b sub n. So let's assume that you know b sub n converges. If sum of b sub n converges, then if the limit of a sub n, as n goes to infinity, of course, of a sub n over b sub n equals 0, a sub n also converges. And so the reasoning for this is that if b sub n converges, that means it goes to 0 quick enough that no matter how much of it you add, you never get past a certain number. And so if you take another function, a sub n, and you divide it by b sub n, and you still get 0, that means that b sub n is infinitely bigger than a sub n. Because like if a sub n over infinity times a sub n, that goes to 0. That means the bottom is infinitely, if it equals 0, that means the bottom is infinitely bigger. And so if we know b sub n converges, then that means a sub n also converges. In fact, it converges way faster than b sub n. But both of them converge. So the second scenario is if the sum of all b sub n diverges, if the limit as n goes to infinity of a sub n over b sub n is equal to infinity, and I want you to guess what's going to happen. So this means that a is infinitely bigger than b. And so if we know that b is already too big to converge and it goes off to infinity, that means that a is way bigger than that. It's way more divergent. So a sub n also diverges. And so the third possible scenario is if a or the sum of all b converges, and limit as n goes to infinity of a sub n over b sub n is just equal to a number or a constant, any number at all, then both converge. And the reason for this is the following. So let's say that the limit as n equals infinity of that is equal to 5. What does this mean? It means that A is 5 times bigger than B. And so if we know that B sub n converges, that means way out here on the infinite number line, and you have B, and B is continuously shrinking. And all the area under it adds up to a number. It converges to a certain number. So this is B sub n. And if you have A sub n up here, which is always 5 times bigger, like here, it's times 5. Here, times 5. Here, times 5. It's always 5 times bigger, which is what the limit's telling you. Well, if all the area under B sub n is equal to just a number, then A sub n, which is always 5 times bigger, is just going to be 5 times that number. If like B sub n is equal to 4, for example, and A is always 5 times bigger than B, then the sum of all A sub n is just going to be that 4 times 5. It's going to be 20. I should clarify because what I just said wasn't entirely true. So, like, if this section of B sub n, starting at like way, way, way out there, like this is essentially infinity and beyond. So if you take this section and this section of B sub n, like the sum of that, from like infinity to beyond infinity, B sub n equals 4, then here, because only here A sub n is 5 times it, then infinity, infinity beyond A sub n is going to be equal to 5 times 4, which is 20. However, before this point, A sub n might be like 1,000 times bigger than B sub n, but it doesn't matter because all of this, like on B sub n and A sub n, doesn't matter. Like this could be 100 quintillion. All that matters in an infinite sum is the end behavior. Does it eventually stop growing? And so this is, what I'm drawing here is the point where they essentially stop growing, they're slowing down. And so this section, like if B eventually slows down and stops growing, then A might be 5 times bigger at that point, but it's also going to slow down and stop growing. So that's all the scenarios for the limit comparison test. Okay. So now we move on to the ratio test. So again, there are 3 possible scenarios for the ratio test. So the ratio test tells us that if the limit as n goes to infinity of A sub n plus 1 over A sub n, and what this means is just the next A sub n in the sequence divided by the previous one. If the limit of that is less than 1, the sum of A sub n converges. If it is greater than 1, the sum of A sub n diverges. And if it's equal 1, A sub n may converge or diverge. We don't know from this test. And so the reason for this is, and let's show this one first. So if you take the harmonic series and you draw out its end behavior, so you're going to have the line y equals 0 here, then you're going to have 1 over n. Well, as it gets way, way, way far out here, like let's say this is where n equals 10,000. This is going to be 1 over 10,000, and then 1 over is going to be 1 over 10,001. But think about how small the difference is in height between these two. This is approaching a straight line. And as you go further out there, it'll only get closer and closer to a straight line. If you get to a googol, 1 over a googol, and then 1 over a googol plus 1, those are almost the exact same number. It's almost a straight line between them. And so if you add up all the area under a straight line, no matter how low that straight line is, the area under that straight line is going to be infinity. Now we know that this is slightly less than a straight line. And so it's impossible to tell if the area under it is infinity or if it eventually settles down on a number. But if the limit is equal to 1, which is the case with this, I guess I should have drawn that. So you have 1 over n plus 1 divided by that. This is equal to 1. And so in the case of 1 over n, where the limit's equal to 1, we don't know, because it's just a straight line. It could be infinity, it could settle down. And so now in a different case, where the limit is less than 1, the reason that this has to converge is if we take a function, a sub n, whose limit is less than 1. For example, the sum of all 1 over 2 to the n from n equals 1 to infinity, the limit of these terms in ratio to the previous one would be 1 over 2 to the n divided by that, which gives you 1 over 2. So the ratio, as you go out to infinity, of each term to the previous is 1/2. The terms are getting half as big as the previous one as you go on. And if we draw that, it looks like this. So you have your line, and then you have your graph of this function, which is continuously decreasing. And if you look at this one at n equals 10,000 right here, the value of this at n equals 10,000 is 1 over 2 to the 10,000. But then if you go 1 over, you get 1 over 2 to the 10,000 and 1, which is a lot smaller. In fact, this is half as big. And then you go over 1 more, and you get 1 over 2 to the 10,000 and 2. And so each time it's getting way smaller. It's not flattening out. And so this graph is constantly decreasing. It's going down, it's going down, it's going down. And if you were to zoom in right here and blow it up, you'd find it's still going down. It's constantly crashing at an appreciable rate. It's falling at an appreciable rate, and it never flattens out. And so it doesn't have the potential to have infinite area because it's never a straight line. And so if we look at the last case where the limit is greater than 1, I think it's fairly obvious why that one has to diverge. Because what that means is if a sub n plus 1 over a sub n is greater than 1, that means that the next one in the series is getting bigger. And so like if your function's continuously getting bigger, if you add up infinitely many of those, it's just going to shoot off to infinity. And so this one's pretty obvious. This one flattens out. We can't tell. And this one always decreasing at an appreciable rate. And so the area converges to a real number. So now the root test. So the root test is a test you can only use in very specific circumstances, but it's very powerful. And so you can only use the root test where you have the sum of a function a sub n where a sub n is equal to some f of n all raised to the nth power. And so what the root test tells us is that if as the limit as n goes to infinity of just the f sub n part, if that is greater than 1, then the sum of a sub n diverges, and if it's less than 1, a sub n converges. And so the reason for that is this. So As n goes to infinity, that means you're multiplying f of n times itself infinite times. And so if f of n, if the limit of that, if the limit of f of n is, 0.999 even, but it's less than 1, 0.999 times itself infinite times is just going to get smaller and smaller and smaller, and in fact, it's going to be 0. And so what you're going to end up with is that a sub n goes to 0 at an appreciable rate, and so it's going to converge. However, if f of n, I guess I should say limit as n goes to infinity of f of n is greater than 1, or like 1.00001, if you take 1.00001 to the infinite power, no matter how close to 1 this is, that's just going to get bigger and bigger and bigger and bigger, and so this is going to be infinity. And so if f of n, if the limit of that is greater than 1, and then its exponent is infinity, then a sub n is just going to get huge, infinite. It's never going to converge to anything. And so that's what the root test tells us. It's a pretty simple test, actually. And it helps us get rid of an exponent. Like if we have, n squared plus 1 over 5n cubed plus 3, and all of that to the n, I don't even know where I'd start with that. But luckily, you get to ignore the n there. You just get to focus on the f of n, because that's all that matters in this case when n is equal to infinity. So now our last test, the alternating series test. So the alternating series test is another pretty specific one, but it's far more intuitive, I believe, than the root test, and you can show it visually. So the alternating series test is used when you have the sum of a sub n, where a sub n is equal to -1 to the n times some function of n. And so there's only two scenarios in this test. If the limit as n goes to infinity of just the f of n part is equal to 0, then the sum of a sub n converges. And if the limit is not equal to 0, if it's equal to anything else whatsoever, then the sum of a sub n always diverges. And so what I really like about this test is that you can understand it visually. So if we take a function f of n, like 1 over n, now you may recall that if you just add up all of 1 over n, it diverges. It's called the harmonic series. However, the limit of these terms is still 0, which means it will converge by the alternating series test if you put a -1 in front of it. And so the reason for that is if we imagine adding up all these terms. So when we take n equals 1, because you can't start at n equals 0, because then you'd have 1 over 0. But if we start at n equals 1, our first term is going to be -1 to the 1, so -1 times 1 over 1. So our first term is going to be -1. So we're going to subtract, we're going to go down. But then our next term, when n equals 2, is going to have -1 to the 2, which is just +1, times 1 over 2. And so now our sign has flipped. We are now adding instead of subtracting. And so this arrow goes back up a little bit. But then our next term alternates back. It's negative again. -1 to the 3 times 1 over 3. So we go down. And I'm sure you'll see that your sign's just going to keep flipping with the powers as n goes up. And so your arrows are going to keep bouncing back. They're bouncing back a little bit, but they dampen. They get smaller each time. And so you're going to converge on some number around there in this case. And any time your limit of f of n is 0, the arrows are going to keep getting smaller, and so they're not going to bounce back as much each time. So it's going to have to settle down. However, if your limit is not equal to 0, then I'm sure you already see that like your first arrow may go down this much, but then your next arrow is going to be bigger. So it's going to start here and go past where it began. And then your next one's going to be bigger again, so it's going to go past where that one started. Then this one's going to go past where that one started, and past, and past. And you see it just grows and grows and grows forever. And so there is no limit here. The terms just keep getting bigger, it keeps bouncing up and down. There's no limit that this sum approaches. And so that's why the alternating series test has to, if the limit of f of n is 0, it has to settle down. And if the limit is not equal to 0, no matter how small these arrows are, they're never canceling each other out. So it just grows in magnitude. And so that's all the convergence and divergence tests, and I hope I made them intuitive enough. Yep. See you later.